Hello there. Today I'm going to be presenting my final project for data mining regarding telecom fraud detection via call graph analysis. Alright, so what is telecom fraud, right? So let's talk about the problem. We've all been there. Your phone rings, you don't recognize the number, you answer it, and suddenly, someone's telling you your car's extended warranty is about to expire, annoying. But telecom fraud goes way beyond just being annoying. In this project, I focus on three main types, right? First is one-to-gear fraud. Fraudsters make one-ring calls to hundreds of numbers. Victims call back, hitting premium rate lines that charge by the minute. Robocalling, automated dialers blast 200 to 400 calls per hour from a single number. Targets are bombarded with scam pre-recorded messages. Call spoofing. Attacker masks, their caller ID to impersonate legitimate numbers, then calls victims in rapid, concentrated bursts. All right, then. So yeah, those are the three main types. But the thing is, what makes all three hard to catch is that traditional rule-based systems fall apart the moment fraudsters, change their behaviors even slightly. So everything just breaks down, whatever rule-based system they have implemented once they change their behavior. So why graph analysis, right? So as we can see here, almost 39 billion is lost to telecom fraud per year. 227 million robocalls are placed daily, and that's just in the U.S. And 72% of carriers lack real-time detection. So what inspired me to do this project was I came across a research paper called Call Mine, published at the ACM conference in 2023. Calmine is a framework that applies graph mining and anomaly detection to million scale call graphs to detect fraud and visualize suspicious behavior, right? So reading the paper was honestly the moment this project clicked for me. The idea, that you could take something as messy as billions of phone calls and turn it into a graph where fraud just shows up visually was really compelling to me. In our approach, we treat graphs as we treat calls as graphs, also detect fraud through behavior. Um, so the graph structure captures who calls whom and how often. Patterns are invisible to protocol rule engines. We also apply some unsupervised learning. No labeled fraud data required to adapt to new attack patterns automatically. So yeah. And of course, when it came to call me, they implemented millions of nodes, and I was just working with about 520. But the method is still the same, and the results are pretty clean, I would say. So the data overview. So when it came to the data overview, I think we used, well, I used a call detail record data set from Kaggle, which composed of about close to 45,000 call recorded, about 45,000 call recordings spanning, I think, 90 days. Yeah, as it says here, it's almost like 50,000. Here it says 50,000, just rounded up. But yeah, essentially it was close to 50,000. Um, and there were about 520 unique users, 500 normal, 20 fraudulent. Um, that's about 3.8 of all users are fraudulent in this data, and which is pretty realistic for a real telecom company as a networks. So yeah. So now let's look at the comparison on the right side. This is honestly my favorite part of the whole project, because the numbers are pretty different between normal and fraudulent users. So normal users call about 3.6 hour calls per hour. Fraud users 135 calls per hour. That's 37 times more. Normal users also have average call durations of 179 seconds. That's about 3 minutes. While fraud users average 17 seconds, barely enough to say hello before hanging up. Uh, so yeah, as you can see, the numbers are drastically pretty different between the two groups. And which is why this is my favorite part. As you can see, normal users call someone roughly every 25 hours. Fraud nodes call someone every 4 seconds. Every 4 seconds. At that point, you're not even making a phone call. You're just assaulting the phone network. So as you can see, the data is just drastically different. Again, I just want to emphasize that. So let's go, and when it comes now, we're looking at the call graph visualization. The data. Here, the actual graph we built from the data. Red nodes are fraud users labeled F001 and so on. Blue nodes are normal users. Even without knowing anything about this graph, you can just look at this and go, yeah, those red ones look different. They're sitting in the middle of the graph with edges shooting out in every direction to tons of different blue nodes. Yeah, so as you can see, you can tell why, in the previous slide, this, is kind of related because as you can see, fraud users are just going everywhere. Um, as you can see, normal users, by contrast, have more balanced connections. They call people, people call them back. They form little clusters with people that they might actually have a relationship with. The fraud nodes don't have relationships; they have targets, and and the graph makes that pretty clear, I would say. So this the feature distributions, normal versus fraud. Data. So now these, all right, now let's look at now these box plots are where the data really tells a story. On the top left, I'll degree, uh, how many unique people each node calls, right? Fraud users go all the way up to 400. Normal users are tightly clustered around 78, not even close. On the top right, short call ratio, the fraction of calls under 5 seconds. One fraud node has a ratio of 1.0, meaning every single call it made was under 5 seconds. So yeah, everyone, it never once had actual conversation. On the bottom left, the inter-arrival mean. As you can see, the gap between consecutive, which is the gap between consecutive calls. Normal users are around 90 seconds and about 25 hours between calls. Um, fraud nodes are basically at zero on the scale. They don't pause, they don't rest, they just call. That's the fraud nodes. Uh, on the bottom middle, calls per hour. Fraud nodes hit up to 300 per hour. Normal users never get above 10. These features again just separate the two groups. They absolutely obliterate the boundary between them. So yeah, right now we're just gonna look at the method. So just here's like the pipeline overview. I mean, so we load the data, build the graph, extract the features, and normalize them. Run isolation forest, run DB scan, combine them into an ensemble. Clean. I would say it's pretty clean and it runs pretty fast on the iTower cluster. Uh, I wanted to point out on step 7 that the ensemble is basically the system saying, if either of my two detectors think something is wrong, we flag it. It's like, having double security basically. So yeah. So the method, uh, yeah. So here we have the graph construction, the call graph construction, the module one. Um, so the graph is a network X directed graph, as you can see here. So yeah, and meaning edges have direction from caller to callee. Every unique number is a node. Every unique phone number is a node. Every call record is an edge. Yeah. So when the same users call each other multiple times, we don't create duplicate edges, we accumulate them. The edge stores total counts, total call count, total duration, and time steps of every call. This is what lets us compare those, temporal features later. So I think our final result was about 520 nodes and 42,410 edges. I don't think it's mentioned here, but yeah, a pretty dense graph for 520 people, which honestly makes sense when you have fraud nodes calling 100 different people each. So here is the feature extraction, right? We pull 13 features per node, 7 static graph features, things like how many people a node calls, how many call it back, raw call volumes, and 6 temporal features, um, calling time, burstness, and short call ratio. The short call ratio deserves pretty special mention because it's simply the fraction of users outgoing calls that lasted under 5 seconds. So yeah. So everything goes through a standard scalar normalization before the model sees. So a feature with values in the hundreds doesn't bully features with values between 0 and 1. So yeah. So isolation forest. So the idea is simple. I would say it builds 200 random decision trees for each node. It randomly splits on features until that node is isolated alone in its own partition. Anomalous nodes with extreme, feature values, they get isolated very quickly. Normal nodes take many more splits because they blend in the crowd. The anomaly scores reflect how many splits it took. Low score isolated fast, which is fraud. High score took forever to isolate. Normal users just living their life. And we set contamination to 5% to match our expected fraud rate and parallelized across all CPUs basically. So yeah. So DB scan clustering. Uh, so any node too far from any dense cluster gets labeled noise. As we can see, the cluster -1, we treat those nodes as predicted fraud. So yeah, the beautiful thing about DB-scan is that it requires no assumption about how many clusters exist. It just finds them naturally, and it catches outliers that have a different shape and feature space than isolation forest catches. The ensemble logic is simple. If either model flags or you're flagged, we'd rather have a few extra false alarms and then miss a single real fraud case. So yeah, just as you can see how it works. The core points, nodes unreachable from any core point as labeled clusters, which is equal to -1. Cluster -node ones are declared outliers and predicted fraud. Yeah, so just as what I mentioned. So here we get to the confusion matrices. So isolation force on the left, it caught all 20 fraud nodes, every single one, 0 false negatives. It did 6 normal users incorrectly, 6 false alarms out of 500 users. That's I think that's a point. I think when I saw it, I think it was like just a slightly above 0.2 false alarm rate. In the real world, that means 6 people get a call saying, "Hey, we flagged your account," and after a quick review, they're cleared. Which is totally manageable. The DB scan on the right is more consecutive, only 3 false alarms, so higher precision, but it missed 8 fraud nodes. It caught 12 out of the 20, so yeah. But if you put them together in the ensemble, you get the best of both. 0 missed fraud and only 6 false alarms. That's the reason, and yeah. But I don't think it was here. So now we get to the anomaly scores. This histogram is probably the cleanest. I would say the red bars are fraud. They cluster on the left side of the chart between -0.5 and -0.10. Blue bars are normal nodes. They pile up on the right between 0 and positive 0.17. There is 0 overlap. You could draw a line between negative, anywhere between 0.05 and 0, and you would fish catch every fraud node without touching a single normal one. Yeah. So the metric summary basically. So this is how everything performed. So as you can see, the isolation forest is basically 100% recall, zero false negatives, and the DB scan 80% precision, but 60% recall, and some 100% recall, 74% precision. Um, and when it came to F1, of it was uh it was about 85%. Yeah. So in fraud detection, recall is a real king. A false positive means analysis makes a phone call. A false negative means real fraud goes undetected and someone loses money. We choose to optimize for recall, and the results back that up basically. So some of our takeaways, or what we've learned, especially number one, graph structure reveals things that per call analysis never could. The call graph basically handed us the answer before the models even ran it. Two, the ensemble approach works. Two models, different strategies, combined output. It's not really revolutionary, but it's effective. Number three, I would say, is a short call ratio is an MVP feature. If someone's making hundreds of calls and none of them last more than 5 seconds, they are not trying to have a conversation. It's just fraud. Number four, there's always a precision trade-off of. There's always a percentage trade-off. 77% sounds imperfect, but in context, it's completely acceptable. 6 false alarms, it's nothing. And number five, future work would look at graph neural networks like Graph Sage, which could learn even richer patterns from the graph structure itself. So yeah. So but for now everything is good. I would say it never great on the cluster, and I'll take that, and that'll be all. And thank you.